Hello. Today we're talking about the mean value theorem again. We're going to look at graphs so you can kind of visualize what it means a little better. So for number one, we have that lovely cubic function and its graph below. There's a value between 3 and 7 at which the tangent to the graph is parallel to the secant line. And that just means that the average rate of change equals the instantaneous rate of change, or the slope of the tangent line equals the slope of the secant line. So we first are going to draw the secant line and the tangent line. I'm going to do my best to draw straight lines. Let's see, I don't know that I have a ruler, but I can use maybe the edge of my planner. We'll see how this goes. So we're going to draw the secant line and tangent line. So the secant line will be through, because we're looking at 3f of 3 and 7f of 7, so it'll be through these 2 points. See if this will work if I set my planner on top. Nope. Sorry. It's watching me struggle with drawing straight lines. This is fairly standard. Yep, that's not going to work. Can't use a straight edge. Okay, we're just going to try to draw it. Okay, there's my secant line. Okay, so now I'm going to draw the tangent line, or try to draw a tangent line that's parallel. So if I try to draw a tangent line that's parallel, looks like it'd be maybe there. So let's say C is about there. Okay, so C is about 5.5. Okay, so MVT applies because we have our tangent slope and our secant slope. There's a point C where those slopes are the same. And is F differentiable on 3 to 7? It is. Is it continuous all the way through? It is. Okay, so basically C existed and also MVT applied. So now we have two values between 1 and 7 where MVT applies. So first we'll draw the secant line, and you're welcome to pause at any point and just kind of try this on your own too, and then come back. It's up to you. There's our secant line. Then we can draw two different tangent lines. So we can draw this one down here, and we can draw this one up here. Again, please, give me grace as far as my well, as far as my line drawing skills go. So we have a C down here. We have a C over here. Okay, so we have 2 points, and really we're just drawing parallel lines, right? So the secant line from 1 to 7, and then we looked at the tangent, points of tangency, so to speak, where the slopes were the same. And so we have one C that's about, I don't know, 2.3 maybe. But again, definitely a rough estimate, and your lines are probably better than mine. Then maybe this other C is like 5.6. Okay. And was F differentiable? It was. Was it continuous? It was. And again, as far as differentiable, we're just looking for, like, is anything weird happening? Are there any holes, asymptotes, cusps, corners? And again, this is just kind of demonstrating what MVT means in terms of graphs. So over here, we have another function. Let's draw a secant line through 1g of 1 and 5g of 5. So I have my points. Draw a secant line. So if I try to draw a, well, you know what? Let's follow the the order, right? We did this. Is g differentiable between 1 and 5? No, it's not, right? Because at that cusp at 4, it's not differentiable. It is continuous though, right? Because we can draw without picking up our pencil or pen or stylus in my case. So yes, it is continuous. So there's no value between of x equals c between 1 and 5, where g prime of c equals the slope of the tangent line. And the reason why is because if you try to draw a line parallel, what happens is it ends up going right through that cusp. So that's the point C, but you can't take the derivative at a cusp. So why is there no value of x equals c that works, where the derivative equals the slope of the secant line? Because you can't take the derivative at a cusp. Okay? So again, this is graphically why MVT does not apply. Okay, so from 1 to 4, same graph, different spot. So we'll draw our secant line between our points that are given. We'll pretend that's straight as, yeah, I'm gonna try that one again. That one's real bad, huh? Okay. I don't know if that's better, but we'll pretend. So now we'll look at where the tangent line is parallel to the secant line. So if we just draw a parallel line, maybe like that. So maybe C is about there. Okay, so there's our C. So from the graph, C is about 2.7 maybe? And again, I'm kind of just guessing. I know it's between 2 and 3 for sure. Is G differentiable on the open interval? Yes, it is. So a graph can have a cusp, and it's not necessarily a problem. It has to do with where it is. So it is differentiable from 1 to 4, and it is continuous from 1 to 4. So MVT did apply. So now we have a piecewise function. So same sort of idea. And if we look, it's a piecewise function. It's not continuous everywhere, which may or may not be a problem depending on the interval we're looking at. So first we'll draw our secant line between from 5 to 7. And so our secant line looks like this. Okay? And then if we try to find the tangent line, the only place where we can have a parallel tangent line that hits the graph, or that intersects the graph, or tangent to the graph, is right there. Okay? And then if we look, is this function differentiable from 5 to 7? Well, 5 to 7, it's differentiable. That's fine. But is it continuous on the closed interval? No, because there's a hole right here. Okay? So there's no value x equals c in the interval from 5 to 7 for which h prime equals the slope of the secant line because the function is not continuous. So now we have the same function again, and we're looking between 5 and 9. So I'll draw my secant line. And then I'm going to look for a tangent line. And so if I make a parallel tangent line, it's kind of hard perspective-wise to draw it, at least for me. So it's something like that. So maybe C is right there. So, I mean, looking from 5 to 9, open interval, is the function differentiable? Yes, it is. Is it continuous? No, it's not. Okay, because of that hole again. So it's not continuous on the closed interval. But there is a point C, which is about 5.8. So the point of this problem is even if MVT doesn't guarantee that there's a point where the slope of the tangent line equals the slope of the secant line, it still might exist. It's just not guaranteed by MVT. So now we have the same graph one more time. So here we have the line between 1 and 5. So right there, can't draw it through that 5 because there's a hole. And so then we're showing that there's a point C where the derivative equals the slope of the secant line. So if we draw a parallel line about there. Oh, that doesn't even look remotely parallel. Okay. Okay, not bad. Kind of bad. We're gonna leave it anyway. So let's say C is maybe right there. Okay. So C is about 3. So now is H differentiable from 1 to 5? It is. It's an open interval. So between 1 and 5, it's differentiable. H is continuous from 1 to 5 because essentially if you're going from 1 to 5 closed interval, you're ignoring all of this over here. So from 1 to 5, it exists at 5, the endpoints are fine, they exist, and it's continuous in between. So that's why it works. Okay, so this is kind of an abstractish lesson, but the purpose really was just to show you what MVT looks like graphically.